All right, welcome back to The Explainer. If you've ever been frustrated because your favorite AI chatbot completely lost its mind and couldn't remember a conversation you just had last week, well, you've experienced today's topic firsthand. Now, if you've been following the headlines, you've probably seen all these massive claims about artificial general intelligence, or AGI, being right around the corner. But today, we're going to cut through that viral social media hype. We're bridging the gap down to the highly technical, absolutely fascinating machine learning breakthroughs that are actually making it possible. We're talking about the cure for AI amnesia. So here's our roadmap for today. We're going to cover 1. The continual learning bottleneck. 2. What is catastrophic forgetting? 3. How humans build memory. 4. The sparse memory breakthrough. 5. How localized updates work. And finally, 6. The missing pieces of AGI. Let's dive right in. Starting with Section 1, the continual learning bottleneck. If we're talking about true AGI, experts frequently point to continuous learning as literally the primary hurdle in the field today. This issue actually gained intense visibility recently after a quote from Elon Musk about the upcoming Grok 5 model. He mentioned that dynamic reinforcement learning is important and that Grok 5, like smart humans, will learn almost immediately. And neutrally speaking, he's hitting on a massive point here. Think about it. An AI system capable of real-time adaptive cognition, without needing to be paused, taken offline, and retrained with static weights, could theoretically trigger a self-accelerating intelligence explosion. Every single interaction would instantly make it smarter. But getting to that point requires solving a massive historical flaw in how AI is built. And that brings us to Section 2. What is catastrophic forgetting? Let's look at the fundamental barrier that's kept real-time learning completely out of reach for years. The core issue here is a phenomenon known as catastrophic forgetting. Basically, this is when an AI model overwrites and completely loses its old knowledge as a direct result of being trained on new information. Currently, large language models just cannot keep learning safely. Every single time you update one with a new batch of facts, you're running this huge risk of entirely wiping out or corrupting the skills it already has. Now, you might be wondering, well, why not just add more storage space? It doesn't work like that, because AI models don't store facts in a neat, organized hard drive where you just drop in a new file safely. They store knowledge inside millions of tiny, fragile mathematical connections. So updating an AI is more like repainting on the exact same canvas over and over. The new paint mixes with the old, and inevitably, those crucial details are lost forever. For instance, if you train a model to be a grandmaster at chess, and then you teach it how to play checkers, suddenly it becomes great at checkers, but it completely forgets how to play chess. Moving on to Section 3, how humans build memory. This creates a really sharp contrast with our own biological learning. AI researcher Dwarkesh Patel recently shared a fantastic analogy that hits the nail on the head. You see, human intellect relies on building context over a continuous time horizon. Imagine you're teaching a kid to play the saxophone. They blow into it, hear the sound, and instantly adjust their technique in this seamless, continuous feedback loop. But current AI learning, it's completely static. If an AI was the student, it would get exactly one attempt to play that saxophone. The second it fails, the entire system completely resets. You'd literally have to write out detailed instructions of what went wrong, feed those instructions to a brand new version of the student from scratch, and have them try again. AI is stuck with out-of-the-box abilities and isolated prompt feedback, which is wildly different from how human memory compounds. Okay, Section 4, the sparse memory breakthrough. This is where things get super exciting. A newly published scientific paper is attempting to solve this exact bottleneck. The paper is titled Continual Learning via Sparse Memory Fine-Tuning, and it outlines a groundbreaking method to essentially stop the AI from scribbling all over its entire metaphorical notebook every single time it learns one new fact. Check out these numbers on the screen because the mathematical contrast here really proves how superior this sparse memory method is. When learning new info, traditional full fine-tuning causes a massive 89% performance drop on older tasks. It basically nukes its old skills. Even highly optimized methods like LoRa still suffer a 71% drop. But this new sparse memory technique, only an 11% drop. That is a real game changer. The AI successfully retains the vast majority of its past knowledge while perfectly integrating the new data. So how are they pulling this off? Section 5. How localized updates work. Let's look at the mechanics beneath that 11% retention metric. The secret here is extreme precision. When new data arrives, the system doesn't just blast those updates everywhere. Instead, it uses what's called a TF-IDF-style ranking score. In plain English, this means the system hunts for the most unique,
highly specific keywords in the new data and matches them directly to specialized memory folders, purposefully bypassing all the generic ones. Once it zeroes in on the perfect match, it updates only those top slots. We're talking maybe 32 slots out of a million available. And most importantly, it keeps 99.9% of all the other parameters in the neural network completely frozen. It touches absolutely nothing else.
And the crucial point here is that this beautifully mirrors human biology. When you learn a random new trivia fact, you don't rewire your entire brain to store it. You just lock those new patterns into specific, localized areas. Sparse memory fine-tuning shifts AI from being the static, globally rewired model into something much more agent-like. It simply opens up new, empty memory drawers and tucks the files away safely rather than burning down the whole filing cabinet every time a new document arrives. But we have to remember, memory alone isn't the finish line. A Google DeepMind advisor brought up a great point recently. Merely storing facts safely is just step one. To reach true, open-ended intelligence, what we really want is a system that generates new learning challenges for itself, learns from them, and then tackles the next problem forever. Bridging the gap between a system that just securely remembers and a system with an open-ended algorithm driving its own curiosity, well, that's the next massive hurdle.
Which leads us perfectly into our final section, Section 6, Missing Pieces of AGI. Does this brilliant memory breakthrough actually mean AGI is imminent?
We definitely need to stay grounded here. Fixing memory stability is a massive achievement for sure, but it represents just one single piece of the intelligence puzzle. Sparse memory fixes the AI's hard drive. It turns the AI into a remarkably clever, infinite notepad. But guys, a notepad, no matter how infinite, does not possess conscious reasoning. It doesn't have emotional modeling, and it completely lacks internal motivation loops. In fact, if we dropped this exact system into a real-world, unsupervised environment today, it would eventually hit some serious roadblocks. First off, there are physical limits. This method assumes you can just keep adding memory slots forever, but eventually, you're going to run out of compute space. Second, what about intentional forgetting? Part of human intelligence is the ability to abstract knowledge and purposefully throw away unimportant noise. This system hasn't learned how to do that yet. And finally, it's still tightly bound by supervised limits. The updates in the paper rely on perfectly human-labeled Q&A data. The AI isn't walking out into an open-ended world and discovering truths completely autonomously. It still needs us to hold its hand and feed it the problems.
So we have absolutely discovered a mathematically proven way to fix the AI's hard drive. We've effectively cured its amnesia. But I want to leave you with this question. Is a perfectly stable memory actually enough to spark true, self-accelerating autonomous reasoning? Or is an infinite memory simply an infinite library, just sitting there, waiting for a conscious librarian who hasn't even arrived yet? Thank you for exploring this with us today, and I'll leave you to ponder that exact gap.